Welcome to this thermodynamics lecture on Introduction to Energy and Introduction to Work. Actually, it's Introduction to the First Law of Thermodynamics and Introduction to Work. We'll talk about energy in here as well. The picture you see on your screen, let's go ahead and look at that, is of a race car, and what I really wanted you to focus on in this picture were the wheels. You see this kind of bright region there and a bright region there, and what you're seeing there is actually the wheels heating up and starting to glow due to friction between the brake pad and the brake rotor. So in these high-performance vehicles, they tend to brake hard, so they decelerate rapidly, and the brake pads do a lot of work on the brake rotor, and it increases the temperature of that brake rotor, causing it to glow. And that concept is part of the first law of thermodynamics, as we'll talk about a little bit today. So that's why I included the picture. We'll do a little bit of analysis related to the picture later in this lecture. So we're going to talk about the first law of thermodynamics, just an introduction. We'll have some more lectures that really go into the first law in much more detail. The same sort of thing with work. We're gonna just introduce it here. We'll have other lectures that go into it in a lot more detail. So let's go ahead and get started. First thing we're going to do is just introduce the first law of thermodynamics. Like I said, you're going to see this many times. And what the first law of thermodynamics really is an energy accounting expression. So you might be familiar with conservation of mass. Conservation of mass is just a mass accounting kind of expression, that mass is always conserved. With the first law, it's essentially like energy is conserved. It's just energy is changing form. Okay, so let's take a look at this first expression. You'll see what I'm talking about. The left-hand side here, this is the change in total energy of the system. So this is change in total energy. That's what the E is of a system. So the E is the total energy. The delta just means a change of. And of course, system, you can see, is just given by the subscript there. That's equal to I'm going to focus on the top expression here. This one is the energy added, or the energy into the system via heat transfer. The Q is the symbol we typically use for heat transfer. So we can transfer energy between a system and the surroundings using different methods. Those two methods are heat transfer and work. Okay? And we'll talk more about each of those a little bit later. We'll introduce work this lecture, spend more time on it in the next video lecture. Heat transfer we'll talk about in the lecture after that. But we can put energy into the system via heat transfer. So you can see the subscript into system. And so you can imagine if we put energy into the system via heat transfer, we're going to get a positive change in the total energy of the system. That makes sense, right? Now the next term is the work done by the system on the surroundings. So this one is the work done by the system on the surroundings. Right, so this is, so again, we have two methods of transferring energy. One's via heat transfer. This one is via work. So perhaps the system is doing some work on the surroundings, and if it does that, then there's some energy leaving our system, and that would cause the total energy of the system to decrease. That's why we have a minus sign here, is if the system is doing work on the surroundings, it's decreasing the total energy of the system. So you can see that we have this energy accounting. We have the energy of the system. We're asking ourselves, how does that energy change? Well, if we put energy in via heat transfer into the system, then it's going to go up. If the system is doing work on the surroundings, then the energy is going to go down. So it's just energy accounting. And by the way, for an energy flow diagram, this kind of corresponds to the following. If that's our system, just some arbitrary blob of matter, then this would be the Q into the system. Right? We're putting some energy into that system. And then this would be our work done by the system. It's leaving. And again, the change in total energy of the system will just depend on whether we're adding a lot more heat or removing some small amount of work. It's the accounting part of it. So this expression that I've written out here that I'm highlighting, That's the form of the first law that we'll use very frequently for systems. Remember, a system is a particular quantity of matter chosen for study. It's all the same molecules. It's always the same substance that we're analyzing. Underneath it, highlighted in, I'll highlight it in green here, is just another way to write the first law. The only difference is I've done the subscript here, the work done on the system. So if we're doing work on the system, so let me redraw the picture. So here's our system again. Here's the heat into the system, energy via heat transfer into the system. And this, notice the arrows in the opposite direction. This is the work done on the system. If the work is being done on the system, then you can imagine that it's going to increase the total energy of the system, right? I like to think about it in this green method here just because the signs are all the same. That if I put energy in via heat transfer, if I do work on the system, then my delta E, my total energy of the system, is going to increase. It just makes more sense to me that way. The reason you have the negative sign here, that's the more traditional way, is because in the early days of thermodynamics, the first law was applied to systems that generated power. It generated work, generated power, and so it was always, you were always getting power out of your system, and so it was written in this form just because that was the most common type of application. But I think it's a little easier to understand if you write it this way. You can do either way. What I do recommend that you do is you always put the subscript into system or by system, into system or on system. As long as you put the subscript there, there's no ambiguity about it, and if you think about the concept, if I'm doing work on the system, if I'm putting heat into the system, then the total energy should increase. If you think about that concept, you won't get mixed up with the signs, okay? So don't try to memorize the equation. Try to just memorize the concept, and then the equation will follow. So this is the first law of thermodynamics written for a system. We can also write the first law of thermodynamics for a control volume. Remember, a control volume is a particular region in space that we're analyzing. So mass can come in and mass can go out. It's just a volume in space. And so here's the expression for the first law for a control volume. So let me just highlight. I've written it again a couple different ways. So here I'm highlighting it here in yellow in the form that you normally see, and then in green that corresponds to the form that where you're doing work on the system. So the way to interpret this equation, so what we have is our control volume. And keep in mind that we could have some mass coming in and some mass going out. Okay, so this is the time rate of change of total energy in the system. So we're now dealing with rates of change in this form. So this is the rate at which energy increases in the control volume. So rate of increase of total energy in the control volume. That's equal to the rate at which we add heat, or we add energy into the control volume via heat transfer. And you'll notice that I have, instead of Q here, I have a Q dot. The dot just represents the time derivative kind of quantity. It's a rate of change. So this is the rate at which we're adding heat into the control volume, or the rate at which we're adding energy via heat transfer into the control volume. Notice I still have my subscript. So then this next one is the rate at which the control volume does work on the surroundings. So this, again, is just similar to the term that I have up here. It's the rate at which work is being done by the control volume on the surroundings. So we have a negative here because that means some energy is leaving our control volume. The dot here just indicates that it's a rate quantity. By the way, the rate at which we do work is also known as the power. We'll come back to that in just a little bit. So far, this equation up to this point looks very similar to what we had before, except we're dealing with rates of change rather than just total change, a change in total energy, a magnitude of energy transfer via heat transfer or work. Here we just have the dotted time derivative quantities. Now, what looks different in particular are these additional two terms. These two terms are for dealing with the mass transfer. Remember, in a control volume, mass can come in and out of the control volume. So I've kind of drawn that here. The m dot is the mass flow rate. It's the rate at which mass comes into or out of the control volume. So it'd be like kilograms per second. So let's say there's a mass flow rate here coming in. And, you know, there's a little piece of substance. I'll just draw it as a little cube here, some mass. And as it comes in, it brings in its own, excuse me, let me fix that. As it comes in, it brings in its own energy. So that little quantity of matter there has its own total energy that it brings into the control volume with it. So I'll just write down that little bit of total energy as, let me write it as a little e. This is the specific total energy. The specific total energy, if you recall from a previous lecture, it'd be the total energy per unit mass. Okay, so specific quantities are the quantity per unit mass, so it'd be the total energy per unit mass. And so I use a subscript E rather than a superscript E to indicate that it's a specific quantity. So this, you know, we have some mass that's coming into the control volume and it brings in its own little bit of total energy. So when that mass comes into the control volume, the total energy of the control volume will increase. That's why we have a positive here into the control volume. So that makes sense that the rate at which the total energy in the control volume changes, it will be positive if we bring in mass with some total energy. Now we have a summation here because there may be more than one place where mass is coming in. Maybe it's coming in there, maybe it's coming in here, maybe it's also coming in here. So we'd have to account for all of those different locations, those three locations in the summation. Do it for location 1, location 2, and location 3. Similarly, we have mass that may be leaving the control volume. So there's a little piece of substance that's leaving, and it's taking its total energy with it. It's removing it from the control volume. So when it does that, it's heading out of the control volume and it's removing total energy. So that's why we have a negative, that the total energy in the control volume should go down because we're taking some energy out of the control volume. So that's why we have that negative. And again, we have a summation because maybe there are multiple places where there's mass going out. So that's the first law expression for a control volume. You'll use this frequently in the course. The green highlighted expression is exactly the same, except all I did is I just like what I did up here, I wrote a plus the rate at which work is done on the control volume. Again, I strongly recommend you always write these subscripts so that you can make sure you get your signs correct. Okay, and just think of the concept. Don't try to memorize the equation. Think of the concept. So if you're still a little wobbly on the first law and what it all means and such, don't worry too much about it. We're going to come back to it multiple times throughout the course, and I guarantee you by the time the course ends, you should understand the first law pretty well. Okay, but at this point, we're just introducing it, so this is your first introduction. Now, let's focus on this top expression, the top yellow expression for now, and you'll see that there are three quantities that we've introduced. We have a total energy term, we have heat transfer term, and a work term. So for the rest of this lecture video, we're going to focus on the total energy term and the work term and introduce those. We'll save the heat transfer term for a different video lecture. Okay, so let's talk about that total energy term. So now there are different types of energy, and the total energy is just summing all those different types together. The three types of energy that we're going to deal with are what are known as internal energy. It's related to the temperature of our system. Kinetic energy, which you're already familiar with, that's the energy associated with the macroscopic movement or bulk movement of the system. And then potential energy, which is the movement of the system in a gravity field. Okay, so those are the three we'll focus on, and they're written here. So here's our change in total energy of the system. This is the internal energy, so U is internal energy. Let me just say a little more about that right now. So the internal energy is, well, you know what, I'll come back to it in a moment. Just let me finish and then I'll come back to it. KE is the kinetic energy. and PE is potential energy. Those are the three that we're going to worry about in this class. There are other kinds of energy. Okay, so for example, there's nuclear energy. So energy associated with splitting the nucleus of an atom, for example. Now, we're not going to worry about that in this course because most of the engineering situations we encounter don't involve nuclear reactions. So the nuclear energy just would remain constant. So it's not changing. And notice this equation involves deltas, so changes in. So we don't worry about that. Similarly, there could be energy associated with chemical reactions. So changing, electrons and, different chemical reactions between atoms and such. We're not going to worry about those. So we're not going to deal with chemical reactions, but they're another form of energy that could be included in this list. Instead, we're going to worry about kinetic energy, which you're already familiar with, right? You should know this from physics, like 1/2 mv squared, where m is mass, v is velocity. This is the energy associated with the macroscopic or bulk movement of the system. So if you've got a system, let's say it's a balloon filled with air. Now, if that balloon is moving, then it'll have some kinetic energy, right, equal to 1/2 mv squared. If it's just sitting there in one place, the balloon has 0 kinetic energy. But if you think about it for a moment, inside the balloon there are all these little atoms or molecules bouncing around inside there, right? So all these molecules bouncing around, and they all have this kind of random movement. There's kinetic energy associated with that random movement, right? Each molecule has its own kinetic energy, and if you summed all those together, you would get what's known as the internal energy. So that's what this term is right here, the delta U. The delta U is the kinetic energy associated with the random movement of the molecules. This kinetic energy is the bulk kinetic energy, kind of the average kinetic energy of the thing as it moves. Okay? So this internal energy is actually related to the random molecular movement, which is in fact related to the temperature of the system. So the delta U, it's sufficient for the time being. All you need to think about is the delta U. It's going to be related to the temperature in some way. And in fact, it could be related to temperature and pressure or temperature and specific volume. You'll see more of that later. But for now, it's just sufficient to say, the internal energy is going to be related to some other variables in the system, one of which is very likely to be temperature. In a future set of videos, we'll talk about how to find that internal energy for different substances, like water, for example, or ideal gases, for example. But for now, we won't worry about that. And of course, potential energy, you've seen before. It's like mass times gravity times height above some reference point. So like this would be gravity pointing down this way, and h would be the height above some 0 reference point here. So that would be like a potential energy, right? Just here's the object itself with some mass times gravity, some force acting downward. We'll come back to that in a moment. But you should be familiar with kinetic energy and potential energy already. Internal energy might be something a little bit new. And again, there could be other items added to this list, but in general, like chemical energy or atomic, nuclear energy, but those are things we don't deal with in this course, so we're not going to include them. Now, below that equation is the same expression for the total energy, but just written in terms of specific quantities. So this is the specific total energy. That's the specific internal energy. Let me just write that one down, because we're going to use it a lot. This is the specific total energy. That would be specific kinetic energy. And there's the specific potential energy. Remember, specific quantities are just that quantity per unit mass. So like the specific internal energy would be the internal energy per unit mass, right? So like the specific kinetic energy, if I look at this expression up here, it would just be 1/2 v squared. And the specific potential energy would just be g times h, as I've written it there. Okay, so you'll see our expressions using these specific quantities often, so I just thought I'd share it with you here. So that's our brief introduction to energy at this point. And again, in future lectures, we'll talk more about how to find, for example, this internal energy term. Okay, so now let's move on to an introduction to work. Okay, so you've probably already had some exposure to calculations of work through a physics course. If you haven't, don't worry about it too much. We'll cover it here. And I also put amp power here because the rate at which we do work is known as the power. So the power is the time rate of change of the work. So the way one calculates work is it's a force dot product over the displacement that the force is acting over. So for example, if I had some system with some force acting on it as a vector. By the way, I've shown the vector here with an over arrow. That's a very common way to see vectors kind of early in engineering. As you get more advanced in engineering, people tend to go to a under tilde. So let me redraw that. So it's like drawing a little squiggly line underneath the symbol. That just means it's a vector. In textbooks and stuff, you'll often see vectors written as bold-faced quantities, but I can't really do that easily on the screen here. So you have this force, which is a vector, acting on the system, which I've just kind of drawn here as a blob. And that acts over some distance, some displacement, I'll just write as ds, just some small displacement. Now, notice I wrote a d here. There's a d here. The d just means a small amount. It means a differential displacement, a very, very tiny amount. And we do that because maybe as I move that object around, I move it in some weird path, and the direction changes. So if the direction changes, then the vector components are changing. So I want to just do it in small little increments so that the vector component's well defined over that small displacement. And then I can find the work by just taking the force dot product with that displacement. And remember, it's a dot product. It's not multiplied. It's actually a dot product. So the force on the system dot product with the displacement, and that gives me a small amount of work acting on the system. Now you'll notice that the d over on the work, I said it's a small amount, but here I use a delta rather than a d. And that's just a notational thing that we use. We put a delta here to indicate that the work is a path-dependent quantity. And I'll show what I mean by that in just a moment. Okay, so I'll come back to that. Now this is just the small amount of work over small displacement. If I want the total amount of work on that system over some finite displacement, then what I have to do is I have to add up all these little bits. And when we add those up, that's called an integral. So that's the integral here. So the work done over some larger displacement is the force as I move from my location 1 to my location 2, dot product with all the little displacements to get from that point 1 to point 2. And I do that over and over again over the whole path that I've taken to go from point 1 to point 2. And that'll give me my total amount of work. Now to just convince you that the work is actually path dependent, and hence the use of this delta, imagine we want to move this block on a surface from location 1 to location 2 here. And that distance, let's say, is L. So I just want to move it from one location to another, and I'm going to apply some force on it. And that force is required to overcome frictional force acting between the block and the plate here, the surface. The friction, if I say the block has some weight W, then the frictional force will be the friction coefficient mu times W, where W is the weight of the object. So if I just go straight across and I calculate the work for that, I'm not going to go through all the steps, but if I find the work done on the system being my block, then when I calculate, so the force on the system, that force will just have to balance the mu times W. I'm going to push it very, very slowly. So F and mu W are exactly equal, right? The force I'm pushing with exactly equals the frictional force to resist it. And so that force is equal to mu W, and it's acting in the same direction as my displacement. So this will be a positive dot product, and it's going over the distance L. So you know what? For this case, I'll just go ahead and write it out. The force would be mu times W, acting in, let's put this is my positive x direction. It'll be positive. It'll be in the positive I hat direction. The displacement will be a dx in the I hat direction because I'm moving in small increments this way. So it's in small little x increments. So that's my ds vector is right there. My force vector is that. Remember, the F is balancing that. I do the dot and then the distance I'm going over is x goes from 0 to L. So when I evaluate that integral, it'll be mu times w integral dx, because the mu and w are just constants, so they can come outside the integral. So x goes from 0 to L integral dx, so that'll just be mu times w times L. Okay, so that's the work that I'm doing on that object to move it from one side to the other. Okay, now let me do the same idea. I'm going to go between the same two states, 1 and 2, but now I move the block and then I bring it back and then I take it back over. So it's actually going back and forth. Right? And I'm still going this distance L. So my point is that we start and end in the same place. But if you notice, the path is different, right? I go back and forth on this. And if you calculate the work for this case, it'll be 3 times mu times w times L. It'll actually be larger because I've had to go back and forth, 3 times. And so you'll see that even though I'm at the same state, like my initial state and my final state are exactly the same, I get different values for work because it depends on the path that I've taken to go from location 1 to location 2. The path is important. So that's why we use this delta to indicate that it's path dependent. So when you evaluate the work, you need to know what path you're taking to get there, okay, from your initial state to your final state. One last thing I'll say about work is the rate at which work is done is called the power. You know what? Apologize. I think I've probably should drop that down there. That should hopefully be a little easier for you to see. The rate at which we do work is known as the power. That's just the dw dt, and that's actually I should change that instead of dw. I'll use my little notational delta w over dt. And typically that power would be like force. Well, I'll just leave it like this. Usually, like the little bit of work would be like the force dot product with the velocity, rather than a small increment in velocity rather than a small displacement. Okay. So you've dealt with power before, I'm sure. Okay, so you can see that the work term is one of those terms that shows up. Let me go all the way back. That shows up in the first law expression. Okay, so now we've introduced the change in total energy. We've talked a little bit about work. And again, the Q, the heat transfer, is something we're going to talk about in a different lecture video. But you can see that the work and energy are closely related to one another, right? So I can show that a little more clearly in a couple of examples. So here, let's take a look at the work required to accelerate an object. So we have this object, our system. It's indicated by the dashed line. It's an object with mass m, initially at velocity v1. And I'm going to apply some force to accelerate it up to velocity v2. Got a little coordinate system in here as well. So my state 1 is here, my state 2 is there. And I want to find out how much work it takes to accelerate the object between velocity from velocity 1 to velocity 2. So the work on the system, again, is going to be the expression of the force dot product with the displacement as I go from state 1 to state 2. And the force that I'm going to have to use to accelerate the object, if you just think about Newton's second law, force is equal to mass times acceleration. Here the mass is a constant, so it's just force times the mass times the acceleration. Force is equal to the mass times the acceleration. So this expression will look like mass times the acceleration. The acceleration would be just the change in velocity with respect to time. And that's going to be in the positive I hat direction. So that's the force that we're applying. And so that's my F. And the displacement I'm acting over is just a little bit in the x direction. So that'll be a dot product times dx in the I hat direction, because I'm going in the positive x direction. So that's my little bit of displacement. Now, the displacement I'm going to write in a slightly different way, and the reason I'm going to do that is because here I'm dealing with velocity and time, and this is position, but I know velocity, time, and position are all related to one another. So I'm going to rewrite dx as the velocity times a little bit of time. Right? We know that a small, if you take the velocity times the time, you get a distance. Right? So I'm just trying to get everything in terms of the same variables. So if you look at that for a moment, you'll see, we've got a divide by dt and a multiply by dt. So this really ends up becoming mass times dv I hat dot product with v I hat. So, and the velocities, since I have the dv quantity here, I need my limits in terms of velocities. So I'm going from velocity 1 to velocity 2. So this will look like the following. When I do the dot product I hat dot I hat, that just that comes out to be 1, and so I'll get m. Mass is just a constant. I can pull it outside the integral. So I'm going to get v times dv. Integrate that, and then that'll just be 1/2 m v2 squared minus v1 squared. So the work required to accelerate that object is just equal to the difference in the object's kinetic energies. So the work required to accelerate it is equal to the difference in kinetic energies. And just kind of quickly going back to the first law, you can sort of see that the change in the kinetic energy is equal to the work being done on that system. Right? So I just wanted to show you that they're closely connected. You can do the same thing relating potential energy to the work done to lift an object in a gravity field. So here we have this same object with weight m times g. G is pointing down, it's acceleration due to gravity. And we're going to move that object upward, positive z direction, distance delta h. We can do the same sort of thing, the work done on the system. It's integral as we go from state 1 to state 2 of f dot ds. In this case, the force that we have to apply to move that object upward is equal to the object's weight, right? Because the weight is what's acting downward, so we have to apply a force upward to balance that. So that force will be mg, this case k hat. This is the force we have to apply upward to balance the object's weight, which is acting downward. And so that force is upward in the positive k hat direction. And then we're dot producting that with the small displacement in the z direction, which would make it a dz in the k hat direction. So that's our ds. So when we evaluate this, oh, and by the way, since we have a dz, that means we're integrating with respect to the z variable. So this will go from z1 to z2. So when we evaluate that, that'll come out to be mg times integral dz from z1 to z2, which is just mg z2 minus z1, which when you look at the picture, that distance is the delta h. So this just comes out to be mg delta h. So you can see that, again, we have this connection between energy and work. The work that we're doing on the system balances the the potential energy change that's occurred in the system. So I just did these simple examples just to kind of give you an idea that work and energy are connected to one another. Okay. Let's do one last example. I don't have it exactly written out here in the notes, but it goes back to the picture here of the race car with the hot brake rotors. Okay, so let's do an analysis of just a typical disc brake. So the way a disc brake works, and maybe I can do it right here. You've got a rotor, which is just basically kind of a plate, a circular plate. This is inside your car wheel, so like your car wheel might be like this. Here's the road. So this is, let's call this the radius of a tire. Let's call this the radius of the rotor. And so as the car tire spins, let's just say it's spinning around with a speed omega. As it spins around, the rotor's spinning as well, and when you press on the brakes, there's a series of hydraulics that compresses a rotor, which I'll just draw it like this. It's like a brake. This is the brake pad. It's just a piece of material. There's one on the front and one on the back, and they squeeze the rotor to slow down the speed of the wheel. It's very similar if you've got a bicycle with hand brakes and you squeeze those, it'll cause these kind of rubber pads on your wheels to clamp onto the rim of your bike tire to slow it down through the action of friction. Same idea for a car tire, except it's, of course, much larger loads and torques and stuff being involved in it. So this is our brake pad. And this is our rotor here. And I'm going to say the brake pad has some area A on it, and I'm going to just say that it's located at, typically they're located pretty close to the edge of the rotor. So I should have probably drawn this to be, I didn't really draw it that well, but it should have been kind of closer to the edge here. Okay, so what I want to do is I want to calculate the amount of power applied to the rotor when we step on the brakes, right? I want to calculate how much power is being generated. And I'm going to do it for some typical conditions. So like the radius of a tire, typical radius might be something like 8 inches. For the radius, the diameter would be 16 inches. If you convert that over to metric units, that's about 0.2032 meters. The radius of the rotor, and this is about where the brake pad is located. That's about 5.5 inches. So in terms of metric, that's 0.1397 meters. Now the typical speed that I'm interested in calculating this for would be for a car traveling at 65 miles per hour. So I'm going to say that the car is going 65 miles per hour that way. And so if I convert that over to metric units, that comes out to be 29.0576 meters per second. You can do these unit conversions using Google or some sort of conversion tables and such. The reason I want that is because I'm trying to find the rotational speed of the wheel. And so you know that from your dynamics or physics course that velocity is like omega times r. In this case, the velocity of the car would be omega times r of the tire. So you can calculate what the omega is, and when you do that, that comes out to be 143 radians per second when you do that calculation. And so to get the velocity of the rotor relative to the brake pad here, so I'll call this V pad, the velocity at the pad there would be omega times r rotor. And it's omega because the tire is rotating and the rotor is rotating. They're rotating at the same angular speed. So it's the same omega. And I'm assuming that at the brake pad, the velocity is, the radius at the brake pad is the same as the radius of the rotor. Granted, it goes over some range of radii. I'm just doing this as an approximation. So I'm just saying it's approximately at the same radius as the rotor. And so if you do that calculation, that comes out to be 19.9771 meters per second. Now, so that's the speed of the rotor right at the brake pad as the wheel's turning at 65 miles per hour, or the wheel's turning causing the car to go at 65 miles per hour. Now, when we step on the brake, there's some pressure being applied to that rotor by the brake pads. The typical pressure, it depends on how hard you step on the brakes, but a typical pressure value might be on the order of 1 megapascal acting over that area. And remember, the area of the brake pad is, I didn't tell you the area, but a typical area of a brake pad might be something like 0.003 square meters. So that's kind of a typical brake pad if you kind of imagine, if you know what a brake pad looks like. It's just a characteristic value. And so from these, you can calculate the normal force being pressed onto the wheel or onto the rotor, and that would just be the pressure times the area. So if you do that calculation, this comes out to be 3,000 newtons of normal force. Now if you want the tangential force, because it's the frictional force that is doing the work on the brake pad. Remember, it's the force dot product with a displacement. In the normal direction of the brake pad, the rotor is not going anywhere. The rotor is rotating tangentially. So the rotor is going this way, the normal force is going that way, so they're actually at 90 degrees to one another. So the normal force does no work on the rotor. It's only the tangential force, the frictional force, that's doing work. So the tangential force would be a friction coefficient times the normal force. A typical friction coefficient for a brake pad against a rotor would be about equal to 0.4. So I'll just put a 0.4 for that. So this comes out to be 1,200 newtons for the frictional force. And so then if you want to get the power, which is just the rate of work, it's going to be that tangential force dot product with the velocity. So since they're in the same direction, that's just going to be times a velocity. I'm just getting the magnitude here. The magnitude of the power would be those two multiplied together. And that comes out to be, when you work out the numbers, 23,972.52 watts. Now, I've mentioned in a prior video lectures, we don't typically want to report our final answers to so many significant digits. If you look at this for a moment, we have 1, 2, 3, 4, 5, 6, 7 significant digits. It's too many. It's much more reasonable to report 3 significant digits. So the answer we would report then would be 24.0 kilowatts. So that's the power that's being generated by that one brake pad when you step on the brakes with this kind of a pressure being applied when you're going at 65 miles per hour. It's a significant amount of power that's being applied to that rotor, and it's that power that eventually causes the rotor to slow down. Okay, to give you a kind of a characteristic or feel for what that corresponds to, if you think about old incandescent light bulbs, you know, the ones that you screw in and they get really hot, those typically require 100 watts to operate. So this would be roughly equivalent to 240 old light bulbs. So the power being generated in those frictional forces would be the same amount of power to light up about 240 of those old light bulbs, 100-watt light bulbs. It's a lot of light bulbs, right? So whenever you step on those brakes, you're dissipating lots and lots of power, lots of energy being dissipated per unit time. So anyway, that's why you tend to see, if you're going in a high-performance vehicle and they step on the brakes really hard over time, you know, they'll start to glow because all that energy is going into that rotor and it heats it up. You can see that from the first law expression, that if we're doing this work on the brake rotor, then its energy is going to increase, and part of that energy goes into much of that energy goes actually into the internal energy of the brake rotor, and that means its temperature goes up, and that's why it glows. So you have to be careful of that, because if it heats up too much, you can actually cause your brake fluid to boil, and when that happens, your brakes become very squishy, and you lose braking power, braking ability. So that's something that you have to make sure you cool down the brakes. So they'll sometimes do some venting on it and such, just to make sure it doesn't overheat. All right, so we'll do another video lecture that spend more time on both energy and work, as well as heat transfer, and as well as the first law. This was just really an introduction. We'll come back to it at a different lecture. But for now, we'll go ahead and end it there.